Hello everyone, this is Jack Hasamon. Today I'll be talking about standard data time systems. In this lecture, we add a twist to how we collect standard time. We estimate standard time by calculation. We'll first try to understand why do we decide to estimate standard time. How do we calculate standard time, especially in simple cases? Then we look at some examples. Ideally, we want to measure standard time in practice, but sometimes there are too many different products. Each product has different production processes. Each process may have constant or common time components and individual time components. Measuring all of them will consume a lot of efforts. So it makes more sense to just estimate standard times based on some of the data that we have. To calculate standard time, we need to create an equation that links standard time as dependent variables to parameters that affect standard time, which is independent variables. In reality, there could be many parameters affecting standard time. We will limit to within 3 parameters in this lecture. The equation to link parameters to standard time will be assumed linear in this lecture also. In order to develop the mathematical model, we need to have a set of data available, time measurements as in y, and known values of parameters as in x sub i's. If the standard time y depends on 3 parameters x1, x2, and x3, and we assume linear relationship between y and all x, we can express the relationship between y and x as this equation. B0, B1, B2, and B3 are constants that we need to calculate. Before we try to calculate these B's, let us check first whether each pair of y and xi are correlated. If we have a set of data for y and xi, we can calculate correlation coefficient r by this equation. If r is greater than 0, it means y and xi are positively correlated. Xi increase will lead to y increase in proportion with r. If r is less than 0, it means y and xi's are negatively correlated. If r is close to 0, it means y and xi have little or no correlation. Another simple way to check correlation is to plot to the graph between y and xi pair by pair to see the trend line. What we should be careful is when we try to conclude that y and xi are not correlated. This is a strong conclusion, thus we need to be careful. So how do we know if r is close enough to 0? Given a value of r and let n equals the number of data points for y and xi, we can calculate z value from this equation. Z value represents confidence level. For example, if z comes out to be 2.1, we are 95 to 99% confident that y and xi are not correlated. Now let us turn our attention to how we find coefficients b in the linear equation. For simple case 1 variable, we have y equals b sub 0 plus b1 x1. If we have n data points, we can add all n equations into this second equation. And if we multiply the first equation by x1 and sum n equation, we will have this third equation. With two equations, we can solve for two unknowns, b sub 0 and b1. For two variable case, we can use similar approach to obtain three equations where we solve for three unknowns, b sub 0, b1, and b2. For three variables, again, we can manage to obtain four equations where we solve for four unknowns. Don't worry, we will see some examples soon. But first, let us summarize what we need to do to develop standard data systems. We need to collect some data which are parameters xi and observe task time y in order to create a database. Then we calculate constant b's. Then we check whether our model prediction is good compared with actual time we observe. If everything looks okay, we can prepare the document outlining how we calculate these standard times, so we can adjust or modify it later on if necessary. Let us look at some example. Zero watcher company makes 8 different watchers, all with same outside diameter, same material. The company collects the time required to produce 1,000 watchers for each internal diameter as follows. If we plot standard time required Y with internal diameter D, ID, we get something pretty close to a straight line. If the company would like to manufacture more different sizes of washer, thus it can estimate standard time for each washer by a linear equation. Here we can calculate everything from the previous data where n equals 8, which is the number of data points. So we can solve two equations for b sub 0 and b1. b0 comes out to be 0.57 and b1 is 0.52. So we can express standard time as a function of internal diameter where t equals 0.52 times id plus 0.57, where id or internal diameter is in inches. Then we check whether our available actual times are within some percentage of predicted times. In this example, we consider an estimate within plus and minus 10% good enough. So we check whether all actual times are within plus and minus 10% of predicted times. All 8 data points fit within plus and minus 10%. If this zero watcher company considers outside diameter and watcher thickness, and if the company has more data points as shown, we can plot graphs to check relationship between standard time and internal diameter, outside diameter, and thickness. From the graphs, standard time is positively correlated with internal diameter, and we have some correlation with thickness. It seems there's no correlation between standard time and outside diameter. We can calculate correlation coefficient R for each pair between standard time and internal diameter. R equals to be 0.67. The correlation between time and outside diameter to be 0.21, and the correlation coefficient between time and thickness to be 0.57. These numbers confirm our assumption, so we do not include outside diameter in our consideration. We can develop linear model for two models. We solve three equations for three unknowns to arrive at the relationship t equal to 0.54 plus 0.43 multiplied by internal diameter plus 2.44 multiplied by the thickness. Then we validate our model by comparing available observed times with model predicted times. Since we have lots of data points, we can calculate percentage difference from dividing actual difference by observed times. Then we calculate the average percent difference, which comes out to be minus 1.59%. Another example, this is a three-variable case. Polka Dot Painting Company is a house painting firm. It is called upon to give estimates for house painting jobs. Based on experience, the company determined that area, perimeter, paint grade, and primer coating requirement all affect painting time. The company would like to develop standard data system to give time estimate. Here we initially have 4 parameters to consider. The company has already collected 9 data points. When we verify the relationship with graph, it turns out that painting area, perimeter, and paint grade are strongly correlated to standard time. Correlation coefficient between standard time and primer coating is relatively small. Thus, we can develop linear relationship as shown in the top equation. By solving 4 equations for unknowns, we get the exact equation. Here, data validation is not shown. Well, this is about what I have to say. If you have any question, please feel free to leave your question in our Google Classroom and I'll be happy to answer them. Thank you and have a good weekend.